this course on computational thermodynamics and kinetics of materials. In today's class, we will see how different properties, thermophysical properties, yield strength, these kind of properties are modeled in Calford tools. These are going to be the contents. Properties in Calford spirit, what different properties can come under this, we will see the list of it first, and then certain properties in that are directly derived from Gibbs energy, we will see them. Then what is this Calford spirit that we are talking about, we will spend a slide on that. Then thermophysical properties which are modeled using this Calford spirit, we will see them with an example of viscosity, and then yield strength, even mechanical properties are brought into Calford tools. We will see how it is done, and we will also see an hands-on example with aluminum scandium system. These are the various properties: thermal expansivity, compressibility, bulk modulus, molar volume, Curie temperature, viscosity, surface tension, electrical resistivity, conductivity, thermal conductivity and resistivity, thermal diffusivity, and yield strength. Among them, these few are directly derived from Gibbs energy: thermal expansivity, isothermal compressibility, bulk modulus, volume. Thermal expansion, thermal expansivity is given like this: 1 by V dou square G by dou P dou T with constant number of moles of elements. Okay. Isothermal compressibility is minus 1 by V dou square G by dou P square with constant temperature and number of moles of elements. Okay. Bulk modulus is inverse of this compressibility. Volume is straightforward, dou G by dou P. You know dG is VdP minus TdS. If temperature is constant, we only have ddP, and that can be rearranged to give this dou G by dou P at constant temperature and number of moles of elements. We will get volume. Right. So these are directly derived from Gibbs energy, but we need to have Gibbs energy as a function of pressure, because we have to do the differentiation with respect to pressure. So therefore, we need Gibbs energy as a function of pressure here in order to do all this. But we usually have Gibbs energy as a function of temperature. If we bring in pressure dependency, then we can get all these properties at various pressures. Right. So now what is this Calford spirit that we are talking about? It is like this: take the experimental data of the property as input. Okay. So the input data is collected and fit it with the model. So model is made and fitting is done. The model should be like the Redlich-Kister model or compound energy formalism, which is just like what we have done for Gibbs energy assessment or mobility assessment. So that is Calford spirit. Okay. Thermophysical properties are modeled like this. The composition dependence is described with Redlich-Kister expression in these cases. Viscosity, thermal resistivity, thermal conductivity is inverse of this. Okay, so only thermal resistivity is modeled, like that electrical resistivity, surface tension. Surface tension is not only done using this Redlich-Kister. There are some other models, Butler, Guggenheim models. The more details of them are there in thermocalc documentation set. We will see about this viscosity and understand how it is done. Viscosity of metallic liquids. Take the experimental viscosity data. So that is the input data, and how the modeling is done. So like this: RT natural log of eta is equal to RT natural log of eta naught plus E. Okay. And this eta is the dynamic or shear viscosity of the liquid. If we want eta, you have to take these things to the other side and figure out. And this eta naught is viscosity at finite temperatures, and E is the activation energy. So if you understand what is the physics of viscosity, you will know that it requires an activation energy and this temperature dependency here. What we will be optimizing is this activation energy. Okay, Redlich-Kister and all will come there. For example, for an AV alloy, okay, RT natural log of eta alloy is equal to XA multiplied by EA plus RT natural log of eta naught A. So it's only for A here. Then similarly for B here. Then this L0 and L1 comes, which are the Redlich-Kister parameters, and this is for the interaction effects. So this part is the n-member contribution or the pure element contribution, and this part is the one which is statistically fitted to input viscosity data and that's for the higher order, for the binary interactions. Okay. Once it is done, we can get this eta alloy. If this eta is taken and divided by density, we get the kinematic viscosity. Okay. So both this dynamic viscosity and kinematic viscosities can come by modeling them like this. Right, that's about the thermophysical properties. Even mechanical properties like yield strength are brought into this. We'll start understanding that. First, let's understand what is this intrinsic strength. Intrinsic strength is the convenience for this modeling. It is basically the strength of n members in the spirit of compound energy formalism. This is what we do with an example. FETAC system will understand this. In that system, FCC phase is modeled as FETI in one sublattice, carbon and vacancy in the other sublattice. Okay. Now, the intrinsic strength is a linear combination as given by the composition. We have done it when we saw about the sublattice formalism. Iron in the first sublattice and vacancy in the second sublattice. If we take these two, it is pure iron in FCC structure. You see, this is FCC phase. And if we take titanium instead of iron, we get pure titanium in FCC structure. And if we take iron in first and carbon in second, it's a FEC phase in FCC structure. It's the FEC phase, iron carbide in FCC structure. Okay. And titanium carbide in FCC structure can also come. If we know the yield strength of these things, okay, they are put into this intrinsic strength using this compound energy formalism. Okay. Okay. The general form of it is like this for two sublattice phase model. Sigma intrinsic is equal to summation over ij, sigma ij, y prime I, y double prime j. This is the sublattice side fractions for these two elements I and j in sublattice 1 and sublattice 2. They are considered like this to get the sigma intrinsic. So basically, what is the contribution to the strength of the phase coming from its n members like this. And to this intrinsic strength, more contributions are added, separate contributions are added depending on the system. Whichever contribution is available in the system, they will come. Intrinsic strength will anyway be there. And grain boundary strengthening, if it is present, it can be added. Solid solution strengthening, precipitation strengthening, or a separate user set constant strength contribution. If at all we know some other contribution is there, we can add some more constant contribution like that as well. Okay. So now what are these things? These grain boundary, solid solution, precipitation strengthening and all. These contributions are modeled with specific models. Okay. Grain boundary strengthening comes from model using Hall-Petch relation. This is the theory to explain grain boundary strengthening. So that is brought here. Then solid solution strengthening. Then solid solution strengthening by this model, and precipitation strengthening is done in different ways. Simplified model is the general one. Seidman model is used for aluminum based alloys, and Repic model for nickel based alloys, and Dashkam's model for again aluminum based alloys. We will see couple of them, the simplified model and Seidman model. How do they match with the experimental data? The details of these models are there in the Thermocalc documentation set. You can go into that. We will see the example and how it is matching with the experiments now. I'm opening Thermocalc. Go to these example files. In the property models here, general, and the first one, property model G04 yield strength. I am clicking on that. Open. Wait for a few seconds. You can see Seidman model results are going to be here, so you can click on this and click perform here. Okay, And you can do the same for this also, strength versus radius in simplified. This plot render also you can click perform. This thing we can remove decision model and its results. We can compare only the other two. Okay, these two things I am removing. Okay. So these two we can compare. Okay. Then click perform in both of them here. Okay. So this is how it is. Experimental data is superimposed. In the simplified model, you can see the precipitation strengthening, the yield strength is given here in y-axis in megapascals. So this is how it goes, and these are the experimental points. Okay, and mean radius in simplified model, that is the precipitate size. Okay, so if the precipitate size is going up like this, and this is how the strength goes up and down like this. Okay, and compared to the simplified model, if you go to this one, the Seidman model, you can see a much better matching to the experimental data. Okay, I'm clicking on this first one, strength versus radius simplified. So you can see it is like this. In this Seidman model, it is very closely matching with the experimental points. Okay, that is the difference between these two models. And the details I'm not giving, as I said, you can find it in thermocalc documentation set. Okay, these models are more to do with the theory of precipitation strengthening or grain boundary strengthening, things like that. It's more of the subject of mechanical behavior of materials to understand all these theories. So the moment there is data, yield strength data, and some models to understand that, if those models are amenable to put into computers, then they can be brought here in this thermocalc software. So that's how these things are done. Understanding these things in a much deeper way obviously will require more understanding of mechanical behavior, strengthening mechanisms, subjects like that. Right. Thank you. I hope the lecture is useful. See you in the next class.